You shine light at an atom, the nucleus acts like a slit. Okay, and what happens when you have a slit that you shine light through? It diffracts, and you get can basically use the equation that we use for diffraction. Sine theta equals the wavelength of that light divided by the distance of the light. From basically, we're talking about, if you remember, we have the central maximum, first minimum, and that's the distance that we're talking about. Okay, so let's use this in a problem. We have a beam of 80 mega electron volt neutrons that are diffracted upon passing through thin lead foil. The first minimum of the diffraction pattern is measured at 12.6 degrees. And remember, well, this is in degrees. Watch out for the radians. This should be in radians. Estimate the diameter of the lead nucleus. Okay, so we know that up here lambda equals sine theta in radians not divided by times d, right? We also know it equals this, and we know the mass of a neutron. Okay, so we can calculate the energy 1/2 mv squared, right? I'm sorry. We have the energy right here. We're going to convert it to joules, and so we get 1.28 times 10 to the minus 11th joules. Okay, this is the kinetic energy of a neutron that is moving really fast based on its momentum. And so we want to calculate its momentum. We find out that it is, that's not it, that is momentum squared, so we take the square root of that, and we get momentum is this meters seconds, and then we can substitute that in up here. We know Planck's constant, we've calculated the momentum, and so all we have to do is divide. Planck's constant divided by our momentum gives us a wavelength of 3.207 times 10 to the minus 15th meters. Now this is in the gamma radiation area region. So this is a very high energy photon that we're talking about here. And nuclei are just like electrons. They absorb and emit certain radiation packages. We don't call them photons, but what they emit is extremely high energy, much higher energy than electrons do. So, because there's a whole lot more forces and things going on inside of a nucleus. So this is the wavelength, very, very short wavelength of the light that is being diffracted. So now we can substitute that in here. We have the angle, and we need to do this in radians, and we have the wavelength, and so we can calculate, just substitute in 3.207 times 10 to the minus 15th divided by sine of 12.6 degrees in radians, and we get 1.47 times 10 to the minus 14th meters. So that is the d is basically the radius of the nucleus.